right, looks like it's going there. All right, and I got everybody's intros that hadn't turned them in last week. All right, if you don't have them turned in, pass them on down. Yeah, and Allison, you're the one that added. Yeah, I'll give you that.
Thank you so much.
Get it back to me by the end of class. Anybody else have an intro for me? All right. You still are taking it out or still need to pass it in, just bring it on it up after class here. We are going to begin with our first actual lecture of the semester. So we're going to start with the chemistry of life. So we're going very, very small to begin with here. So in my lectures, I like to include kind of some key concepts, just to give you kind of an outline of what we're going to go over in the lecture itself. Hopefully all of you have watched that video that I had you guys watch ahead of time. That will come into play very soon here. But basically, just kind of give you an overview of the class and what we will be talking about. There's a lot of levels of organization in biology. All right, so much so that each one of these organizations, you could probably, have a whole semester's worth of information. You could probably have 4 years worth of information just on one of these levels of organization. So this class, we're going very broad, all right? We're not diving too deep into any of these. So I know some of you might know a little bit more than what we're going over. Just know that I expect you guys to know what I'm actually presenting in the lecture. So, like I mentioned, biology can be studied at all levels. Quick side note, I did change some of these lectures to make it a little bit more coherent and shorter. So if you printed them off way ahead of time, it might be slightly different. I tried to update it right before class, and it wouldn't let me for the student version. I will try to update that again, but you might see a little differences, but overall content is the same. All right, so can be investigated. All levels of biology. There are so many different ways you can study biology. I mean, anything from ecology to economic biology. All right, we're so broad, we're so vast, but we're really going to zoom way down into the chemistry of life. All right, so we're starting about as small as we can possibly get, as small as we know. All right, so smallest level of organization is chemistry. All right, so we're talking about atoms, the very smallest functional unit in biology. Now I say functional unit because even though atoms are made of smaller subatomic particles, right, like we saw in that video, electrons, neutrons, protons, atoms cannot be broken apart naturally. All right, so we can break them apart by all sorts of cool physics inventions and all sorts of that stuff that I don't truly understand, but some people do amazing work there. They can be broken down, but it's not natural. All right, so atoms are the smallest functional unit. Now if we combine atoms together, that's when we start getting molecules, and that's what is most common to see in biological organisms. All right, so the atomic structure. You guys all watched that video. Let's go over the atomic structure. And I hope I have a piece of chocolate. All right, so let's start in the middle. What do we call the middle of an atom? Nucleus, yes. And what is in the nucleus? Protons and neutrons. All right, so let's just start. Let's see here. Very, very simple. All right, so protons and neutrons, do they have an electrical charge associated with them? Let's start with protons. Positive, yes. And neutrons, do they have a charge? No, they are neutral, yes. So easy to remember these. Protons, positive, neutral. Oh my gosh. But neutral starts with N, positive starts with P. Very easy to remember those, all right? So we have a positive and a negative charge in our nucleus here. Now outside of the nucleus, we have one more subatomic particle, and what would that be? Electrons, awesome. And what charge do they have? Negative. All right. chart here. Alright, so I believe this is a helium atom. Alright, so we have 2 protons, 2 electrons. This is pretty typical when you look at an atom that the number of protons, number of electrons are going to be equal. Alright, they're canceling out each other's charges to make the overall atom neutral. Now there are some atoms that will not be neutral if they lose or gain an electron. We'll cover that in just a little bit. Alright, so the electrons themselves, I'm actually think I'm going to go back to the slides for this one here because I have a better picture. This does not like me walking away for long periods of time. All right, so here's a nitrogen atom. So we went over the nucleus. We have the protons and the electrons here. We have the protons and the neutrons here. The electrons are on the outside here. Now the electrons, they're going to be grouped. All right, so they're going to be grouped in a couple of different ways. One of them is orbitals. All right, so if we have an orbital, the max number of electrons we can have are 2. All right, so in this picture here, this would be an orbital. All right, so we have a group of 2 electrons, an electron pair. This would be an orbital here. Now we have 3 more orbitals right here, down at the bottom, off to the side here. Those are also orbitals, but they're not filled. All right, so they can have a max of 2, but they can also just only have 1 singular electron. All right, so we can organize these orbitals even further into electron shells. And this image here kind of depicts this as these blue kind of halo spheres around the nucleus here. These would be our electron shells. All right, so the electron shells are going to house the orbitals. How many orbitals they house depends on the atom itself. We're not going to get that in depth when we talk about our atoms. We're mostly going to focus on the atoms that have 1 or 2 electron shells. First electron shell here is always going to be able to contain 2 electrons, so 1 electron pair. All right, that's the max that it can hold. And as we go out from there, the next electron shell can hold up to 8. All right, and this is where we're mostly going to focus our efforts in this lecture, is on those 2 electron shells. Know that it can get very complicated, very big, very fast, but we're just going to focus on the simple atoms here. So as I mentioned, these outer ones you can hold up to 8. You notice that nitrogen, they do not have 8 electrons in their outer shell. All right, they only have, let's see, 1, 2, 3, 4, 5. Yeah, I counted that right. All right, they have 5 electrons in their outer shell. So their outer shell is not full. All right, an outer shell would be full if it had those full 8. So each of these shells have this energy associated with them. So energy, the ability to do work, all right, and the energy that we're talking about here is potential energy. All right, it has the potential to do something. All right, now this becomes important when forming bonds. And the outermost electron shell is really what's going to help form bonds here. So in the outermost electron shell, we have the electrons that we call valence electrons. These are going to be the electrons that will form bonds with other atoms. All right, so in this case, we have 5 valence electrons. We'll get into this a little bit more, but only 3 of these are really going to be available for forming bonds. All right, so there is a vast array of elements. All of you have seen the periodic table of elements, I'm sure. I did change the picture a little bit because the other one did not have good resolution. This one's not much better, but we're getting there. A lot of information in the periodic table of elements. All right, so they're kind of grouped by their similarities. So just kind of very basic overview here. If we look at each row, all right, so going across, this is the number of electron shells that they will have. All right, so we just looked at nitrogen. Nitrogen is in the second row here, and we saw that it has 2 electron shells. So everything in this second row is going to have 2 electron shells. Now the columns also represent something. All right, so the columns are the number of electrons in that outermost shell. So go back to nitrogen because we just talked about it there. We know it has 2 electron shells, and we saw that it has 5 electrons in the outermost shell. All right, makes sense? It's in column 5. All right, so it's kind of a basic way to look at an element and be like, oh, well, how many valence electrons might it have? How easily is it going to be able to make bonds with other atoms based on where it is in the periodic table of elements? You kind of broadly look at it here. So I'm going to have you guys do a group activity. And I'm just going to have you guys draw out an atom, work through everything we just talked about, make sure that these basics are solidified in your head. So this is where we get to the fun part of forming groups. So like I mentioned, we have to form groups kind of based on where we're seated. I'd like to have groups of about 4 people. We can go 1 above, 1 below. Kind of, like I said, group where you're seated. So starting over here, let's see, we have you 2, and then maybe you guys as well would make a good group. You 4 in the corner, I think that's a good arrangement, if that's okay with you guys. All right. I'm going to just make our groups here. This will help them when they do any contact tracing that'll need to be done. All right, let's see. Sky and Noah. Why don't we do Sky, Noah, and Kristen? Does that work? All right. Let's do, trying to think about how group work's going to work in a long row. I don't want you guys to be on the opposite ends not being able to hear each other here. So we have Jenna, Catherine, Yoda, Megan, and Natasha. All right. Would that work for you guys as a group? You guys can kind of clump together and hear each other. And all right, if that doesn't work, let me know and we'll rearrange something. Right, this looks like a natural group to me. Group of 3, does that work? And then group of 4 in that back row. And then we'll do the group of 3 over here. All right, so roughly assigned groups here. If issues arise from these groups, just come and talk to me and we'll work something out. I don't think there's going to be much group work outside of class, but inside class, there's going to be a lot of it. All right, so first group activity, I want you guys to draw an atom. All right, so I'm going to give you 1 of 4 atoms. We'll just kind of randomly split them up here. I want you to tell me how many protons, how many electrons, how many neutrons does it have, how many orbitals does it have, how many electron shells, and is the outer electron shell full? All right, so let's see here. What atoms did I pick? So this group over here, Mia, Astrid, Lakeisha, and Addie. I'm going to have you guys do carbon. Group in the corner here, Ella, Eli, Victor, and Alex. I'll have you guys do nitrogen. Back row, let's have you guys do oxygen. Let's see, Jenna, Catherine, Leota, Megan, and Natasha. Big group here. Let's have you guys, I'm going to have you guys do carbon as well. I'm going to have you guys do helium here. All right, so let's see. Then carbon twice. Let's have you guys in the front, the group of 3 here, do nitrogen. Sarah, Ellen, Bella, and Cecilia, I'll have you guys do oxygen. And then I'll have the group of 3 on the end there do helium as well.
Oh, right. Okay. I guess I have. Vaseline, also.
Great time to ask any questions you don't want to ask in the big class.
Could you go back to
Yes. I want to leave the slide up here so everybody has the questions. But I can probably do a quick copy and paste. Let's see. That doesn't work the best, but let me know if you need it moved at all. Oh, there we go. You guys only need the top row, so top couple rows.
A8A. So it's in row 1, column 8. But it's in the 8th column. Yeah, normally the number of neutrons and protons will be the same. It just has a general rule. I'm not gonna have you guys go yeah. Hydrogen is one of those exceptions. It only has one proton. Wait, what's your name? Crazy. Oh, I have this for you. Awesome. Yeah, my picture on the back of it. Oh, that's what I thought too. I'm like, wow, we have an artist in here. Oh, she knows. Yeah. Alright, I'm getting the gist that
kind of wrapping up here. Anybody need more time? All right, sounds good. So let's dive right in. All right, so who are my carbon groups? All right, close to each other. I like that. All right, so how many protons, electrons, and neutrons does it have? Yes, it has 6, yes. And I don't know if I mentioned this, maybe I forgot to say it, but we know it has 6 because if we look up here, the atomic number is 6. That tells us how many protons it has. All right, and typically the number of protons and neutrons are going to be equal. There's some instances where that's not the case. We're not going to go too much into that. Isotopes would be one. Hydrogen is another. Hydrogen actually only contains 1 proton, no neutron. Like I said, I'm not going to have you guys worry about that too much here. All right, so we have 6. We know that from our periodic table of elements here. What else did I ask you guys? All right, what about electrons? Carbon group, how many electrons do we have? 6 as well, yep. So we're equaling out those charges between the protons and the neutrons. And number of orbitals? All right, let's go over orbitals here. So I'm going to zoom in on the carbon, except I'm struggling to work my PowerPoint. I'm not used to Google Slides. All right, carbon is at the very top. I can't get it any better than what it is. Wish I could. There, that's a little bit better. All right, so carbon. 4 orbitals is what I heard somewhere. Someone said 6, 5. All right, carbon. All right, carbon has 5 orbitals. All right, so how do we know this? We know that an orbital contains a max of 2 electrons. All right, so the first electron shell, if it's full, even if it's not full, it's always going to be 1 orbital. All right, so that one's the easy one. Now we get out to that outer shell. The outer shell can have a max of 8 electrons. So if we have 8 electrons, we could divide it in half to be 4 orbitals if all the orbitals were filled, if we had all the correct electrons in that outer electron shell. All right, so if that electron shell was full, we would have 4 orbitals. Now, in the case of carbon, we only have 4 electrons in that outer electron shell. Now, they're going to be divided up equally here. So each are going to be its own orbital. All right, they're just not going to have an electron pair. They're all going to be singular. All right, so we have 5 orbitals there. How many electron shells? 2, yes. All right. Let's go back to nitrogen. Who are my nitrogen groups? Awesome. All right. How many protons, electrons, and neutrons does it have? 7, yes. How many orbitals? I hear a resounding 5. That's awesome. All right, we got the 1. This picture doesn't do very... doesn't work very well to show electron pairs, but this would be a pair here. So that would be 2, 3, 4, 5. All right, that's awesome. How many electron shells?
2.
And is the outer electron shell full?
Oh, man.
All right. Let's see, oxygen. Where are my oxygen groups? All right. How many protons, electrons, and neutrons does it have? 8. All right. How many orbitals does it have? Let's take a look here. So we got 1, 2, 3, 4, 5. So yes, you guys are totally correct. Again, this picture doesn't group them by pairs, so it can be a little harder to distinguish them. Let's see, how many electron shells? 2. And is the outer electron shell full? All right. And lastly, helium groups. I think helium. All right. How many protons, electrons, and neutrons? 2. How many orbitals? 1. How many electron shells? 1. Is the outer electron shell full? Yes, it is. All right. So a much smaller atom than the other groups here. All right, does that make sense for everybody? Orbitals make sense versus electron shells? All right, so let's keep going here. One other thing I just want to mention about the periodic table is each atom has the atomic number, which I kind of mentioned to you guys here. I should have mentioned to this before I had you draw it. But for example, nitrogen is 7. All right, so we know it has 7 protons. We know that protons and electrons are generally equal. Also has 7 electrons. And we know that protons and neutrons are generally equal, so 7 neutrons. It also has an atomic mass. Now, we're not going to do so much with atomic mass. If you guys are taking chemistry, you'll probably dive into this pretty deep. The atomic mass is that little number right below sodium. You can see how heavy an element is. So for our purposes here, we're just going to generalize and look at atomic mass as in sodium is heavier than hydrogen. All right, we're not going to do anything more with atomic mass. I just wanted you guys to know what that random number was. All right, so lots of elements on our periodic chart here. There really is only a few that's absolutely crucial for human life. All right, so oxygen, carbon, hydrogen, nitrogen, those are the 4 big ones. All right, and if we look at the percentage of all atoms in the human body, all right, it's a large percentage. We are largely made up of these 4 different atoms. All right, now this is where weight comes into play, where I told you, sodium's heavier than hydrogen. If we look at hydrogen, hydrogen is about 63% of all atoms in our body. But because it weighs just a tiny, tiny bit, it's only about 9% of our human body mass. All right, so this is where weight kind of comes into play, just kind of an interesting aspect of biology to look at here. Now, obviously, we're not just made out of 4 atoms. We're made out of many, many more. So there's a lot more trace elements down here. I don't expect you guys to memorize these trace elements. Just know that they exist. They're very important in forming proteins and enzymes and a lot of chemical reactions in our bodies. But they are vastly smaller quantities than those 4 main elements. All right, so we got down what an element looks like, what an atom looks like, how it's arranged. Let's talk about bonds. All right, so a chemical bond is needed to make a molecule. All right, so a molecule is going to be 2 or more atoms bonded together. They can be the same atom, they can be different atom. The technical term when they are different atoms is a compound. It's still a molecule, but you could also refer to it as a compound. The important thing to note about molecules is that the properties of a specific element in a molecule can change drastically with whatever else it's bonded with. All right, so sodium hydroxide, very, very caustic. All right, that's very corrosive. I think it's corrosive, not caustic. Corrosive, I don't really want to touch it. It's not good. It's made out of sodium, hydrogen, and oxygen. All right, it's not good stuff. But that same atom, sodium, it's also part of table salt. Totally harmless. We need it in our bodies. We eat it all the time. Sodium and chlorine. So depending on what it's bonded with, it can totally change how it acts. Now there's 3 types of chemical bonds that we're going to talk about. All right, covalent, ionic, and hydrogen. And they each have different relative strengths. So covalent is going to be the strongest of the bunch here. Ionic, kind of that in between. And hydrogen, pretty weak. All right. Some of you still taking notes. I'm going to keep on moving on. All right. This is highly recommend having the PowerPoint in front of you so you don't have to write down everything that's on my PowerPoint because that can get a little tedious. I understand that. So we're going to start with covalent bonds. In covalent bonds, this is where those valence electrons really play an important part. All right, so this is where atoms are going to share electron pairs. And so this is where we looked at the atoms and asked, is that outer electron shell full, yes or no? It becomes important when we start talking about these covalent bonds. All right, so if the outer electron shell is not full, we can form a bond with another atom. All right, and this is going to be a very strong bond. All right, so covalent bonds, very strong. They're each kind of sharing an atom with, or an electron with each other here. And that's because when these outer electron shells are full, this is when the atom is the most stable, right? Generally speaking. So these atoms, they like to be stable, all right? So they're going to form bonds with other atoms to become more stable. All right, so in our example here, we have fluorine. Fluorine has these valence electrons along the outer edge. One is not in an electron pair, all right? So this orbital is not full. And that has the ability to bond with these single electron and hydrogen. All right, so we're forming a covalent bond. We are sharing electrons. There's many different types of covalent bonds here. I put this image up here just to show you that they can be a single covalent bond. In terms of like water, ammonia, and methane here, they're sharing one pair of electrons in each of these bonds. They could also be double bonds where you're sharing two pairs of electrons. And in rare cases, though it does occur, you can get triple bonds, such as nitrogen. When nitrogen bonds to each other, it creates a triple bond. So they're sharing three pairs of electrons here. Now with bonds, equally shared electrons are going to be nonpolar. All right, and this is going to make more sense when we talk about electronegativity. All right, so electronegativity is the attraction to share electrons. So some atoms are more likely to share electrons than other atoms. All right, and we call those atoms more electronegative. All right, now if the two atoms that are in a covalent bond have the same or at least very similar electronegativities, it's going to be a nonpolar bond. All right, they're sharing those electrons equally. One atom is not fighting for electrons stronger than another atom. All right, they're completely sharing it as equal as you could possibly share an electron. All right, now this becomes important when we talk about electrons that are more electronegative than others. All right, so oxygen here is going to be more electronegative than, say, nitrogen. And the reason I say that is generally those with more protons tend to be more electronegative. All right, so we have oxygen has 8 protons, nitrogen has 7, slightly more electronegative. Much more electronegative than hydrogen, which only has 1 proton. All right, so because oxygen has such a high electronegativity versus hydrogen, when we have a water molecule, for example, oxygen is going to want to take those electrons closer to its atom. All right, so hydrogen is kind of fighting to keep its electron, essentially, because that electron wants to go towards the oxygen. And that's where we get the polar covalent bonds. All right, so this is bonds between two atoms, different electronegativities. And we talked about water here. Here's our image of water. All right, so when we are making a water molecule, we are binding 2 hydrogens with 1 oxygen. All right, so we have our covalent bonds here. Now, because of those differing electronegativities, those electrons are more likely to be closer to the oxygen at any given moment. And that's kind of represented in this picture up in the corner here. It's kind of an electron cloud, all right, the likelihood of where the electrons are going to be at any given moment. And you can see this cloud is much larger around the oxygen. So those electrons are going to be closer to the oxygen more often. And this creates a polar effect, all right? So the oxygen, because it's taking in more electrons than it normally has in its outer shell, all right, it has electrons to spare, so to say. It could stand to lose electrons, which is how I remember these negative and the positive charges, all right? So oxygen is going to be partially negative because it has more electrons than it technically needs because of those polar bonds and how they're sharing it. It could stand to lose some if need be, all right? So that's partially negative charge. Opposite is true for hydrogen, all right? It's essentially giving up, all right, its electron. It's not totally giving up, it's sharing the electron, but the electron's closer to that oxygen. So the oxygen could spare to gain that electron a little bit closer to it. All right, hence the positive here. So the hydrogen has a partially positive charge. So we've created a polar molecule. All right, it has different charges on different ends of the molecule. Now in water, this is very important, and we are going to get to that at the rest of our lecture here, which hopefully we get to. But we're going to move on to ionic bonds. All right. So I told you that generally, all right, the number of electrons are going to be the same as the number of protons because those charges are going to opposites attract, so they neutralize each other. All right, it has a negative charge. Sometimes these atoms can lose or gain an electron. All right, and this is due to how stable the atom is in certain configurations. So our sodium atom here, all right, it can lose. Excuse me, what is sodium doing here? Sodium, I'm not sure why it has that outer ring there. But sodium is losing an electron, kind of a confusing picture. But sodium is losing the electron here and becoming a positive ion. All right, so essentially, it could stand to gain another electron. All right, hence the positive. So if it's a positive ion, we call it a cation. If it's a negative ion, we call it an anion. All right, meaning it has gained an extra electron. All right, now we can gain or lose more than one electrons in some cases. Calcium is a good example of this. Calcium, as our little symbol here, is a 2+. It has 2 extra electrons. Yes?
Where does that electron come from?
Where does it come from? That is a good question. That I might have to get back to you on.
Oh, okay.
Yeah. Trying to think. Electrons can just kind of float around.
Oh, okay.
Where they come from, though, I'm not sure if another atom is losing it. Let me get back to you on that. And I'm going to write a note to make sure that I do get back to you, because now I'm curious. All right, to be continued in that question. All right. Does that make sense with ions? All right. So they can form ionic bonds. Again, same kind of opposites attract theory. In this case, we're looking at table salt, so sodium chloride, and it looks like a whole diagram here of gaining and losing electrons become the different ions. Now, one ion is positively charged, one ion is negatively charged. Opposites attract, they're going to form that ionic bond. All right, so ionic bonds, I think, are kind of the easier types of bonds to understand. So just kind of going back so far what we've talked about. All right, so we have those non-polar covalent bonds. Those atoms have equal electronegativities. All right, so they're not hogging the atoms more than the electrons more than other atoms here. We have our polar covalent bonds, where one atom is going to hog the electrons closer to it than those other atoms in the molecule. And then we have our ionic bonds, right? When different charged ions will come together and form those ionic bonds. Now the last bonds we're going to talk about are hydrogen bonds. All right, so hydrogen bonds occur when we are talking about polar molecules. All right, so think about those polar covalent molecules, think about water. All right, so a hydrogen atom is going to become electrically attracted to an electromagnetic atom in another molecule. Now these bonds are really weak, they're very easily disrupted. And if we look at our water molecule here, if you remember I said oxygen had a partial negative charge and hydrogen had a partial positive charge, or they're polar. That partial negative charge on the oxygen is going to be attracted to the partial positive charge of a hydrogen of another molecule. All right, so molecule to molecule, they're attracted at different ends of their molecules, and they're going to create these hydrogen bonds. Now, as I mentioned, they're very weak. They're very easily disrupted. They're formed and gained all the time, not super strong. They can also occur within a larger molecule. We're we're not going to go into this too much, but I want to throw this out here. So if you've seen these fancy pictures, a lot of chemists will have them, in their slides, diagrams of a protein or something, and they have this 3D structure going on where there's twists and there's loops and turns. Hydrogen bonds can become important in creating those 3D structures. Now, they're not the only thing that's going to necessarily create those 3D structures, but they're very important in some of them. Yes?
Don't hydrogen bonds only deal you can also hydrogen bond if it has nitrogen, fluorine, and oxygen? Isn't that how you know? It's hydrogen.
It has to be, it's a hydrogen bond if it has hydrogen attached to it. So hydrogen bonds can't form between molecules that don't have a hydrogen attached. Whether or not it's an oxygen, nitrogen.
Like hydrogen with fluorine.
Potentially. I think I'm following what you're saying. Yes. So if there's a hydrogen bonded with to a molecule and it's in a jar of other molecules with polar ends to it, as long as there's hydrogen, it can form those hydrogen bonds. Now, it might be bonded with oxygen, it might be bonded with nitrogen. I think those are most typical just because of their valence electrons that they have around in their outermost electron shell. Just because of their arrangement, they're likely to form these molecules with hydrogen more easily. I think maybe that's, if I'm getting your question right here, that's kind of what we're thinking here. And we're going to talk a little bit more about that aspect next week too, especially with carbon, because carbon is an important molecule, or important atom, excuse me. Any other questions? All right. We may or may not finish this lecture today, but that's okay. I had another in-class activity that we might not quite get to, but we will get to that next week. We're going to start with our discussion of properties of water. Don't think we're going to finish here. So, properties of water. Water is this highly important molecule in biology. All right, it's just kind of some terminology that when we're talking about the properties of water, we're going to talk about a solution, we're going to talk about solutes, and a solvent. All right, so a solution is the combination of solutes and a solvent. The solutes being those substances that are dissolved, and the solvent is the liquid in which it's dissolved in. All right, so there's kind of our terminology when we're talking about a solution. If it contains water, it's going to be an aqueous solution, so water is the solvent. All right, so water is that liquid in which things can dissolve. Now, ions and molecules with a polar covalent bond will dissolve in water. All right, so our water molecule, we've been talking about this last few slides here, it's polar. All right, it has an end that's partially negative, and it has two other ends that are partially positively charged. It is a polar molecule. And because it is polar, this allows other molecules that also have some sort of polarity associated with them to dissolve in water. All right, so this can be ions, and this can be other molecules with a polarity associated with it, with a polar covalent bond. Now we call these molecules that will readily dissolve in water hydrophilic. So we're just going to go through the example of table salt here because it's the most common example. I'm sure elementary school we all dissolved water into table salt here. I'm just now realizing that this clock is slightly slow and it is 1:20 and you guys probably have classes after this. So we're going to talk about dissolving of salt next week. One thing before you guys leave, at the end of this lecture, there are videos to watch for next week. We will start on next week's lecture, so make sure you do watch those videos.